Okay, and now we shall define binary relations as subsets, as arbitrary subsets of uh, these Cartesian products. Okay. By definition, we say that a set is a binary relation. This word binary we will usually omit. It's a binary relation given of binary relation uh, of A to B, or better between A R is just a subset of A times B. So what is a binary relation? A binary relation between A and B is an arbitrary subset of the product. Let us obtain some intuition for this concept. First of all, some trivial examples. Assume that A be just assume that A contains just 1, say 2 and 3, and B contains 2, 4, and 5. Then say we can consider the following binary relation between these sets. Say you can have a pair of 1 and 4, 2 and 4, 2 and 2. It is well possible because 2 is present in both these sets. And say 1 and 5. So here it is. It is a binary relation between A and B. Clearly, we can have more examples. We know that we can consider pairs of real numbers as points of the plane, of the coordinate plane, say. We can consider this Cartesian product. R times R. That is the plane. In the plane, what will a binary relation be? What if F is a binary relation between R and R? In fact, that means that R is a figure, some set, some geometric figure in this plane. Here it is. So every geometric figure is a binary relation. Every graph of a function is a binary relation. So whatever set of planar points, say it may have some isolated pieces, say here F3 contains these two isolated points and this segment. All these things are just binary relations between R and R. So every figure may be considered as a binary relation. Is this idea clear? Is it clear?
Yes.
Mm. Okay. Let us have more examples. We say that R is a binary relation on a set A, if and only if R is a binary relation between A and itself. So that means that one can call these figures, these geometric configurations, one can call them binary relations on R, on the set of real numbers. And among these binary relations on A, we can have some important examples. Say the empty set is always a subset of a set. Hence, the empty set is always a binary relation between any sets. In particular, it is a binary relation on any A. If I have this product itself, it is also a binary relation. Why not? And also, in the case when A and B are identical, in the case of binary relations on a set, we have something special. We have the important identity relation. Identity relation. So I say that the identity relation of a set A is, what is it? It is a set of all the pairs of identical elements. So it is a set of all such pairs XX, where X belongs to A. So this is just the set of all pairs of identical elements. For example, let A be the set 1, 2, 3. Then the identity relation is just the following set: 1, 1, 2, 2, 3, 3. Is it clear?
Yes.
And what if we take reals? What if we take reals for our set A? So what is the identity relation of R, of the set of all real numbers? It is a set of all pairs of identical reals. And if you consider that, if you consider that as a geometric figure, what would you obtain? You would obtain this diagonal line, the identity function. So here it is. This is exactly, this line is exactly the set of all such pairs. The identity relation, we can see that, is just this line is a graph of our identity function. Is this idea clear?
Yes.
Okay. For every binary relation, we can find two important sets, which are known as its domain and range. So let R be a binary relation between A and B. So we say that the domain of R, the domain is just the set of all such x's from A such that there is at least one y where xy belongs to R. So what is it? This is just our way to say that x is the first coordinate of some pair in R. So that means that x is the first coordinate of some pair in R. Of course, instead of saying there is a pair in R whose first coordinate is x, we are saying it some other way, quite natural for every mathematician. We are saying that there is y, there exists y, such that xy makes a pair in R. And similarly, we can define the range of our binary relation the following way. It is a set of all such y in B that there is some x for which xy belongs to R. So what is it? Clearly, it is the set of all second coordinates. So y is the second coordinate of some pair in R. We can see that this condition guarantees that y belongs to B. So look, if say there is y with this property, given R is a subset of A times B, that means that y itself, xy belongs to A times B. Hence, y itself is guaranteedly in B, and and x is guaranteedly in A. So that means that if I have this condition, then of course x belongs to A, and this very condition holds. But this thing means that by definition, our second set constructing axiom, that means that our x belongs to this set. Look, anything belongs to this set if and only if, by definition, it belongs to A and satisfies this predicate. So by definition, this is the set of all such x's from A which satisfies the predicate. And anything that satisfies the predicate also belongs to A. Hence, this is equivalent to saying that our x belongs to the domain. And of course, vice versa. So this condition alone is enough to guarantee that x belongs to the domain. So what was the problem? The problem was to secure x being an element of A. But if X is the first coordinate of some pair in R. Provided R is a subset of A times B, this guarantees that X belongs to A. Similarly, if this condition holds, then Y is necessarily in B. So we have proved an easy lemma. X belongs to the domain if and only if there is some Y with XY being an element of R, and similarly, Y is an element of the range if and only if for some X, this pair XY belongs to R. Is this idea clear?
Yes.
Why is it important? Because whenever you see this symbol, whenever you see that something belongs to the domain, you can automatically replace this with this formula. This formula may look more complicated because it contains a quantifier, but essentially it is easier because in this formula we have no new symbol, no this domain symbol. It is just our definition, that is. Okay, and now if we want to consider examples, let us compute domains and ranges for our binary relations. But before that, let us introduce some notation. We say that XRY, much like you would write it down as X is less than Y. We shall see that less than is also a binary relation. XRY, this will stand for just XY, the pair XY being an element of R. So we have saved 4 symbols. These 2 brackets, comma, and this elementhood sign. So XRY means that the pair XY belongs to R. With this in view, let us compute domains and ranges. So assume that we are interested in this our relation. Say this one. What is the domain? What is the domain of R? The domain of R must be the subset of Y for which where every element of which is the first coordinate of some pair. Look, what about 1? 1 is clearly a first coordinate in this pair and this one alike. So the domain of R clearly contains 1. 1 is the first coordinate.
2.
Also, it contains 2. And that's all. All the other pairs have either 2 or 1 as their first coordinates. And similarly, let us compute the range. What is the range of R? It must be the set of all second coordinates, a subset of B. What should we take?
2,
Please name all
4,
the elements
and
of
5.
the range.
2, 4, and
Which ones?
2, 4, and 5.
2. Yeah. 2 is an element of the range. What else?
4
4. Exactly. Here it is. What else?
and 5.
5. Yeah, brilliant. So the range is just the set of all the second coordinates. But what about this example? Our geometric interpretation of binary relations. What is the domain? What is the range? In fact, the domain and the range are just projections of our geometric figures. So look, when talking about the range, we are interested in all such y's, from the set of all reals, for which at least there is at least one x such that the pair x y belongs to our figure, to our set. So that means that the range is just the projection of our set to this axis of second coordinates, to the ordinate axis. Similarly, what is the domain? The domain is just the projection of our set to abscissa axis. Is this idea clear?
Yes.
So the domain and the range are just the projections of our set. And what is the domain of the empty relation? Which first coordinates the empty set of pairs may have? What is the domain of the empty set?
Empty set.
Clearly. What if I take A times B as a binary relation between A and B? What is the domain of that? I have taken all possible pairs. What are their first coordinates?
It's A.
Brilliant. And what about the range?
It's B.
And what about the identity relation? What is its domain?
It's A.
And similarly, the range. The range of the identity relation is also A. You may look at this picture as well. So what is the domain? The domain is the projection to this axis. So it is R. And similarly for the range. Okay. Now we are going to introduce some operations over binary relations. But before that, let us introduce some more useful concepts. I will give an informal definition for the so-called diagram of binary relation. Diagram of a binary relation. So what is a diagram? In fact, I won't give a definition, but just an example. If you define it rigorously, then a diagram would be almost the same as the relation itself. But in fact, the idea is as follows. When xy belongs to R, or equivalently xry, we are going to make a plot. We are going to plot these two sets, x and y, as planar points and connect them with an arrow. And look, the orientation of this arrow differs. The first coordinate from the second one. They are connected with an arrow when this arrow starts at At the first coordinate, its source is the first coordinate and its target is the second coordinate. So let us plot some binary relation with this idea in view. So assume that we have the following one: 1, 2, 2, 2, 3, 2, 4, 5, 2, 4, or better, 2, 6. So how can we plot it? Of course, first of all, let us plot all the points, all the sets which belong to either the domain or to the range. So we need 1, 2, 3, 4, 5, and 6. Do you agree?
Yes.
Now, let us sketch our arrows. We have a pair 1, 2. So we need an arrow from 1 to 2. If we want to depict more than one relation in one diagram, you should use letters to label this binary relation. So you want to say that 1, 2 belongs to R, so that's why you can label your arrow with this letter R. What about 2, 2? Here the source and the target of our arrow do coincide. What should we do? We can draw such a loop. We can draw such a loop, so it is an arrow that comes from 2 and goes to 2. From 3 to 2. One more arrow. From 4 to 5. And finally, from 2 to 6. Is this idea clear?
Yeah.
This is a very nice and practically effective way to depict finite binary relations. Finite means that they have just finitely many pairs. And for infinite relations, you cannot, of course, draw all the pairs, but you can make a sketch which would somehow reflect the bigger picture. So, what are the main features of your binary relation? As an example of an infinite binary relation, let us consider the relation less than. Okay. So assume that we are familiar with the relation less than, with the binary predicate less than on the set of naturals. We know that, say, 2 is less than 3. But it is not the case that 2 is less than 2. Do you agree? Two is less than 3, but 2 is no less than 2. Do you agree?
Yes. Yes.
Okay.
Yeah,
And
yeah.
now, this is a predicate. Look, x is less than y. This is a binary predicate with the domain that is over, say, naturals. And we can translate this binary predicate into a binary relation, into a set. There is a way to consider binary predicates as binary relations, and this way is very easy. Let us take all such pairs xy from n times n, but by the way, for short, I will write n squared instead of n times n. In fact, you can introduce more degrees, say n cubed as n times n multiplied by n. But maybe we shall discuss these things later. For binary relations, they are not that important. So let us take all the elements of n squared, all pairs of naturals, but let us take just those among them where x is less than y. So now we have defined our predicate as a binary relation. Instead of saying that 2 is less than 3, we can equivalently say that 2, 3, this pair, belongs to the binary relation less than. Is this idea clear? I have not defined anything new. I have just give you some other perspective. So we are going to look at our predicates as binary relations, namely the set of all pairs which satisfy our predicate. Is this idea clear? Or do you have any questions?
No.
So let us try to make a diagram. Say, of course, it is infinite, but nevertheless, 0 is clearly less than 1. So we should have such an arrow. 0 is less than 2. But moreover, 1 is also less than 2. 2 is less than 3. 3 is less than 4, and so on. Of course, 0 is less than 1, less than 2, less than 3, less than 4, and so on. 1 is less than 2, 1 is less than 3, 1 is less than 4, 2 is less than 4, and so on. Is this idea clear?
Yes.
Of course, it is infinite, and we have no ability to draw all this infinitely many arrows in a finite time. But nevertheless, this is a sketch. This should reflect the general idea of our relation. But what benefits could this considering of predicates as sets, as binary relations, what benefits could it provide? In fact, this will allow us to apply various set theoretical and some special relational operations to our predicates. Let us introduce such operations. First of all, I will define something special for binary relations. This is called conversion. So let R be a binary relation between A and B. Now I will define the converse of R. What is it? The converse of R is denoted the following way: R to the power minus 1. The converse of R is the set of all such pairs yx, where y comes from the range of R and x comes from the domain of R, where look, x, y belongs to R. So what is it? You can easily rewrite it the following way. Look, yx belongs to the converse relation if and only if xy belongs to R. Or in other words, in other symbols, yr converse x is equivalent to xry. Is this idea clear?
Yes.
By the way, look, our usual formalism that 2 is less than 3 now means just that 2, 3 belongs to our less than relation. Similarly here. Okay, so this conversion operation just swaps the first and the second coordinate in every pair. Let us see what can we have in our examples. What is the converse of this relation R? You should swap 1 and 2 in the first pair. So the first pair of the converse relation is just 2, 1. What about this one? This will transform into
2, 2.
This pair is invariant for this operation. It won't change. 3, 2 is transformed into
2, 3.
2, 3. Yeah, really. 4, 5. 5, 4. And here I would obtain 6, 2. Okay. Brilliant. And what about the diagram? In this diagram, it is enough to change the orientation of every arrow. So now I have 2, 1. This 2, 2 arrow won't change. It will in fact be the same. It will in fact be the same. 3, 2 will transform into 2, 3. 2, 6 into 6, 2. And 4, 5 into 5, 4. Is this idea clear?
Yes. Can I ask something? Hello?
Now, let's more examples. What if I take the identity relation? Let's can you hear me now?
Yes.
No. Apparently, I have some connectivity problems, but nevertheless, let us try continuing. Can you see the whiteboard?
Yes.
Okay. Let us consider converting the empty relation. So we have no pairs. We have no pairs and we have relates in any such pair. So the result will be, what if I convert the empty relation? The result is
Empty relation.
exactly. What if I take all possible pairs between A and B? What if I convert them? The result will be
BA.
Brilliant. What if I take this identity relation? Look, here is of the form 2, 2. Every is identity. What if I object here? Can you hear me now?
Yes.
Okay, so let us try continuing. So what is the converse of the identity relation? Clearly, it is the identity relation itself. Yx belongs to this identity relation if and only if xy belongs to the identity relation, that is, if and only if x equals y. Of course, x belongs to a. Can you hear me now?
Yes.
So excuse me, but I have no means to improve the situation immediately. So was it clear so far? And what do we take the domain of the converse relation? What is it?
Red.
The range of R. Similarly, the range of the converse relation is the domain of the original one. So it must be quite clear for now. And what if we take the converse of this less than relation? What is it?
Bigger than.
Greater than. Yeah, exactly. That's it. Look, let us apply the definition. So we see that yx belongs to this conversion if and only if x is less than y. So we see that this is the same as to say that yx, yeah, look, x is less than y. That is, y is greater than x. That is, yx, our original pair, belongs to this greater relation. But how can we obtain greater or equal? What should we do with this? What should we do with this relation less than to obtain greater or equal? Any ideas?
Can you add the identity?
Add the identity, no, because we should swap the coordinates as well. So here we have less than, and here we have greater or equal. But we know that x is not less than y. We know that as a matter of fact that if and only if x is greater or equal than y. For this is true for whatever naturals. Do you agree?
Yeah.
So in fact, we can take the complement. The complement. If it is not less, then it must be greater or equal. But what is the complement? What is the definition? The complement is our usual operation for sets. But the question is, what should we take as the universe? It is quite clear. If we are considering our R as a binary relation between A and B, where A and B are of course not uniquely determined, but somehow fixed for a moment, assume that we have fixed them, then we are defining the complement of our binary relations the following way: A times B minus R. So these are just all the pairs which are out of R, but nevertheless which belong to A times B. This is the complement. And of course, alongside this complement, we can apply other set theoretic set algebra operations to binary relations. Assume that we have taken, say, the union of two binary relations. What is the converse of the union?
The converse.
The union of the converses.
Yeah, that's it. Not the intersection, but the union of the converses. Let's prove it. It is quite easy. In order to prove two sets to be equal, we should prove that anything is an element of the left-hand set if and only if it is an element of the right-hand set. But we know that both these sets consist of pairs, and in a pair, its coordinates are uniquely determined. So you can uniquely identify a pair with its coordinates. So it is enough to consider a pair of the form xy that belongs to this set and prove that this very pair will belong here. Let's prove it. By definition, that means that yx belongs to the union. Yx belongs to the union. But when anything belongs to the union, when it belongs to the first set or it belongs to the second one, that is, yx belongs to p, or in other symbolism, ypx or yqx. And now we can individually converse both these relations. So this means that xy belongs to the converse of p. Similarly here, xy belongs to the converse of q. That is, xy belongs to the union of the two. Is this idea clear?
Yes.
And what if we take double conversion? What if we converse a relation 2 times in a row?
You got P again.
Exactly. So how can one prove it? It is in fact xy belongs to this set if and only if yx belongs to this one, which is equivalent to xy belonging to p, so they comprise the same pairs. Okay. And what about the complement? It is also quite interesting. Let us consider the interplay between the complement and the conversion. What if we first take the complement and then converse it? Of course, it is important to see to which sets the complement we have. So, look, if P is a binary relation between A and B, then its conversion is, of course, a binary relation between B and A. And the complement of P is just A times B minus P. All the pairs excluding those in P. And likewise, the complement of this set is just B times A minus the converse of P. So we are stating that this set equals what? The complement of the converse. Is this idea clear?
Yes.
Okay. So let's prove it, and then we shall see an example. Assume that xy is a pair from B times A, of course, because we are speaking about the complements. Assume that xy belongs to this set. When is it the case? If and only if yx belongs to the complement. But yx belongs to the complement, given this, of course, if and only if yx doesn't belong to P. But yx doesn't belong to P if and only if xy doesn't belong to the converse. Because if xy, if it belonged to the converse, then yx would belong to P. That is, xy is a pair from B times A. That means that xy belongs to the complement of this conversion. Is this idea clear?
Yes.
As an example, we can compare two binary relations on naturals. let us take the complement of less than and then convert it. What should it be? What is the complement of less than? The complement is
Greater
or
than.
equal.
greater or equal, yeah. So here we have greater or equal converted. What is the converse?
Less or equal.
Brilliant. This was our left-hand side. And what about the right-hand side? What if we first convert a binary relation and then take the complement? What is the conversion of less than?
Greater.
Than.
Greater than. And what is the complement of greater than? If x is not greater than y, then x is
Less than or equal.
less or equal. And evidently, they are identical. Is this idea clear?
Yes.
So we see that considering predicates as binary relations, as sets, we are now able to apply various operations to these sets, to these predicates. This may be set algebra operations like union or intersection or complement, and also we have some special operation for binary relations, conversion. And in fact, in order to provide an algebra of binary relations, which is our goal, by the way, we should define one more operation known as the composition. Composition. This composition is slightly trickier than conversion. So what is the main idea? First of all, let me give the formal definition. Let P be a binary relation between A and B, and Q be a binary relation between C and D. Look, there is no assumption that B equals C. Then I shall consider the following. P composition Q from the right to the left. This is called the composition of P and Q. Look, from the right to the left, we shall see why. Of course, this writing convention is common for some languages like Arabic, but for many other languages, this is strange. So, say in Russian and other European languages, we prefer writing from the left to the right. But here the composition is to be read from the right to the left. Later, we shall see why. The composition of P and Q, what is it? It is a set of pairs, X, Z, where X has been taken from the domain of P, and Z has been taken from the range of Q, such that there is some intermediate point Y where which somehow connects X to Z. So there is an arrow from X to Y via P, and from Y to z, y, q. So essentially it is an existential quantifier. So what we have? Look, assume there is a path of two arrow path. We have a path from x to y, p. We have an arrow, a p arrow from x to y, and q arrow from y to z. By definition, that means that we have one arrow labeled with this composition. Is this idea clear?
Yes.
What are
Yes.
what are the naturals? What may natural interpretations of this composition be? In our real life, we have many situations when the composition is applicable. Let us see it. For example, a friend of my brother. A friend of my brother. Who is it? How can I describe the set of all such persons? Say we can consider two relations, x, p, y. That means that y is a brother of x. And, or let's call it A and B. And similarly, we can consider other relation Q that says that B is a friend of A. So what is the composition? What does it mean? A, B, or better say X, Z, P composition Q. That means that there is some Y, according to the definition, such that X, P, Y, and Y, Q, Z. So that means that there is someone who is a brother of X. Y is a brother of X. And Z is a friend of Y. So the question is, who is Z to Y? Who is Z to Y? Clearly, Z is a friend of whom? Of Y? Of something, of someone, of a brother of X. Is this idea clear?
Yes.
So there is someone, some Z, not specified otherwise. There is some Z who is a brother of X and whose friend is Z. Or you can consider other interpretations. Say, consider two cities, X and Z. You can say that Z is accessible from X via two flights with a change. So now we have two identical relations to be accessible by a direct flight. So say another example. Assume that xpy means that y is accessible from X via a direct flight. So what it means, X composition of P and P, Z. That means that there is some change point, some airport where you should have a change. But here Q is the same as P. X, Y, Z. That means that Z is accessible from X with one change. Is this idea clear? So basically it is about considering two arrow paths. Can you hear me? Is this idea clear? Gentlemen, are you still present?
Yes.
Do you have any questions, or was it clear?
Yes. It's clear.
Okay, I hope so. And we see that, in fact, this condition clearly implies that X in the domain of P and Z is in the range of Q. So we can state the following lemma, the following easy condition, that XZ belongs to such a composition if and only if there is a change point such that X, P, Y, and Y, Q, Z. Please notice that what is written second acts first. It might be strange, but in fact it is a consequence of the way you are denoting functions. Look, for functions, you would write down something like that. Sine of cosine of x is just the result of their composition this way. Written second, acts first. So that's why, in order to be in a good accord with this convention, we have assumed that what is written second acts first. And in order to finish our lecture, let us prove a theorem about this composition. Composition properties. The first and the most important is its associativity. Composition is always associative. That is, if I take a composition of P and Q and then compose that with R, the result will be the same as I take the composition of Q and R and compose P with Z. And the second statement is about the conversion. What if I convert this composition? What is the result of the conversion for the composition? Do you know it, that?
The conversion of P composed with the conversion of Q.
So yes, you should convert both the relations, but change the order in composition. Are you familiar with matrices and their
Yep.
transposes? You know that in matrices, if you want to multiply two matrices and then take the transpose, it will be this product of transposes, change in order. You can compare that. Okay. Now let us prove our properties. For the first one, first of all, let me give a graphical proof. So it is just an illustration. Assume that we have such an arrow. What it means? It means that there is some change point somewhere. Let's call it, assume that this is, say, X, and this is W. There exists some Z. There exists some Z such that we have such a path. But what does it mean? That means that there is some Y, which is such an intermediate point. And now we can just regroup. From Y to R, there is a two-arrow path. First from Y to Z, Y Q, and then from Z to W, Y R. So here it is. That means that there is a change point such that we can move from X to this change point Y. First Y P, and then Y Q composition R. We can move from Y to W. Is this idea clear? Wasn't it clear?
Yes.
Okay, let us give a formal proof. It won't take much time. So what does it mean? It means that there is Z such that X, this composition, Z and Z R W. Now let us apply our property. Let us rewrite this one. What that means? There exists Z, there exists Y such that X, P, Y, and Y, Q, Z, and also Z, R, W. And now look, this doesn't depend on Y. Doesn't depend on Y. So you can move this quantifier out of the bracket. This doesn't depend on Y. So there is Y with such property and something. You can transform it equivalently to the following. There is Y with this property and also satisfying something, because this doesn't depend on Y. This is the trick. So there is Y, there is Z such that XPY and YQZ and ZRW. Of course, you can easily regroup the brackets here because it is just a conjunction. And now this thing doesn't depend on Z. That means that you can move Z into the bracket. It doesn't depend on Z. So you can move that into the bracket and obtain the following. There is y such that x, p, y, and for some z, y, q, z, and z, r, w. And now this looks suspiciously familiar. We see that it says that there is a two-arrow path. First y, q, then y, r, from y to w. That is, from y to w, you can move first YQ, then YR. And the final step is the following. So now X and W are connected with a two-arrow path. So X, W belongs to this one. So XW belongs to this composition if and only if it belongs to this one. Hence, these two sets are equal. Is it clear?
Yes.
And our final argument is in support of this one. It is also very easy. In fact, it will be much shorter. Assume that X and XZ, this pair, belongs to this set. What that means? That means that ZX belongs to P composition Q. So there is some Y such that ZPY written second, X first, remember, and YQX. Brilliant. And now I can individually convert these two. So there is some Y such that Y P converts Z and X Q converts Y. Okay, I have a conjunction, and in this conjunction I can equivalently reorder its members, its terms. So I would obtain that there is Y such that XQ converts Y and YP converts Z. So look, there is a two-arrow path from X to Z, which first goes over Q converse, X, Q converse Y, and then over P converse. So this one equals this one because they comprise identical pairs. Is this idea clear?
Yes.
Do you have any questions? Remember that you can always revisit these arguments with my lecture notes. If you have any questions, you are very much welcome to post them to our chat. Anything else, gentlemen?
No.
Okay, thank you. Please excuse me for these connectivity problems, but unfortunately, I had no way to improve them. Unfortunately, nevertheless, thank you very much. I'm going to publish the video of our lecture soon. Thank you.